linear function, and you guys, you know this. Do we have to show work here? No, because you know this. If I substitute -2 in for x, what am I left with? -2, then what? Then what? 2, good. So I'm going to graph this. Okay, and I could keep going. If I input any x value, I will get a corresponding y value. So, with that being said, what is my domain? Stop it. Good. What is my range? John? Good. Okay, a few of you have asked and looked back at your notes, so thank you. I appreciate that. Intervals of continuity mean if I take my pencil, or in this case my smartboard marker, and put it anywhere on this graph, I'm going to continue. I'm not pulling this pen off, right? Intervals of continuity state that if I had a function that looks like this, there's a break in the graph, so my pen has to leave. This one, it does not. So the intervals of continuity and domain will be the same, okay? So intervals of continuity are always in parentheses, okay? Most of the cases we're going to see here, they're going to be the same because we don't have any jumps in the graph like we see here, okay? If we had jumps in the graph, then you would use the U, okay? And there would be two separate. Intervals of continuity for linear functions are continuous, all right? Where am I increasing? Good, negative infinity to infinity. This graph is not decreasing, okay? So that is your parent function, okay, for linear functions. How many of you knew that? Knew all of this? Figure it all out. Maybe not so much remembering the intervals of continuity, but knew everything else. Yes, okay. So now if we go to number 2 here, okay, and we have our table of values, okay, and I will just start with the negatives showing in parentheses. What do I get? What's -2 squared? Steffa. 4, -1, 0. Good. So graph this function. Okay. How many of you remember, and this just froze, quadratics? A lot of you should, or parabolas. This is a parabola. It's frozen. Okay, which states that if I was to draw a line down the middle of this graph, I would get the same points on either side, okay, because it's symmetrical. You have that axis of symmetry, okay? What is the domain of this? Grace? Good. What is our range? John? Good. Now, intervals of continuity. What would it be? Yeah, you. Good. Because again, if I take my marker, I'm not taking it off the graph, okay? Where am I increasing? Well, good. Where am I decreasing? Yeah, Mustafa. Good. Okay. What's one other thing you could tell me about quadratics? What's one other thing? Yeah. It is a function. The inverse is not a function. Yeah. Okay. This is a function. What else can you tell me? What else do you know? Anything about quadratics? What does the lowest point mean on this graph? There's a name for it. Yes. Good job. Okay. So The vertex is the middle of the graph, either the highest point or the lowest turning point, okay? The vertex is where you always want to start because you will have the same y values on either side, okay? Parabolas, quadratics are always U-shaped, right? How many of you did have number 2 correct? Okay. Next, which might be new to you, is a cubic function, okay? If we have cubic functions, again, -2 cubed, uncubed. Okay. What is -2 cubed? Yeah. -8. -2 times -2 times -2. How about -1? Yeah, Tor. Good. 0, 1, and then 8. Good. Okay. Okay. So this is what it looks like. Again, we're only using a small table of values. What is my domain? Yeah, Sam. Good. What is my range? Jackson. Good. What is my intervals of continuity? Brian. Good. Where is this graph increasing? Charlotte. Excellent. Way to change it. Nice job. Okay. As you read this graph left to right, it's constantly increasing. You guys have seen this graph before on a practice or a homework or even a warm-up where we think that's a constant or a changing point. It's called an inflection point where it's kind of changing directions. Instead of going straight up, it's kind of flattening out then going, but it's still increasing. Okay. We'll get into cubic functions a little bit later in this lesson. So what does this resemble? Can you make any connections for some that we have done already? What is it very similar to? Yeah. Not an inverse. That's okay. Thank you for... What is it similar to? The two graphs before this we just did. What is it very similar to? Yeah, Charlotte. A linear function. It's very similar to a line. Okay? There might be more curves here, but all of this is the same. Okay? It's very similar to a linear function. Okay? Very similar. Okay? That's going to come in handy later on. All right, the next one is square root. Why didn't I give you a table of values with negative numbers? Can't have a negative square root. So, what is the square root of 0? Square root of 1. 4. If I did 9. 3. Okay, so we're going to graph that, which you guys have done already. Okay, so that's our square root function. Bianca, what's my domain? Good. See, Laurel, what's my range? Good. Julia, what's my intervals of continuity? Perfect. We're going to change it. Good job. And again, intervals of continuity only use parentheses. Okay. How about increasing? Emily. Good job. Excellent. Okay, and this one is not decreasing. Okay, good. All right, and the last one. Does anyone remember what the absolute value function looks like? Julia, question? Or? Yep. Excellent. Good job. Absolute value, what does it look like? Yeah. A V shape. Okay. So if I substitute -2 in absolute value, what do I get? 2, -1, 0, 1. Good. 2. Good. Okay. Okay. Absolute value. Lindsay, what's my domain? Good. Finn, what's my range? Awesome. Good. Gavin, what's my interval of continuity? Good. Lizzie, where am I increasing? Awesome. And Joshua, where am I decreasing? Yep. Good job. Okay. So what is this similar to? Yep. Quadratic. So what other piece can we relate this and quadratics to? There. Parabola, which is the same as quadratic. But what else do they have in common? There's another term, yeah. The vertex, okay? They also have a vertex, okay? So these 5 functions, okay, are our family of functions, are the parent functions, okay? This is what we are going to keep referring back to. So you're going to have this pink sheet on your desk, okay? I'm going to pass out the next packet, and with a partner or someone near you, I want you to try this warm-up, okay? Which is number 1 and 2. You have your parent function, f of x equals x, and f of x equals x squared. Plus you have a g of x function for each. I want you to see if you notice any changes. If you do, describe it, okay? So we're going to work on, okay. So for the g of x function for the first one, what are my new values? What are my g of x values? Yeah, Rory. Good. Two, three. Sorry, some of these will go off the graph. Okay, so what do we notice? Yeah. Good, excellent. So same x values. Different y. Okay, so what about the y values? What did you notice? Okay. 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 Yeah. Good. So we took f of x, right? You could look at it this way as well. F of x, and we added 5 to those y's. That's what it looks like, right? So you add 5 to the f of x values. Okay, that's another way. Good. How about, did it move at all? Corey? Good. It moved 5 units Excellent. Okay, so right then, those two graphs, parent function, and then we transformed it. Okay, by adding 5, which means it moved up 5 units. Okay, same x values, however, the y values were different. And with the y values, you added 5 to that. Okay, so now, if we look at our quadratic, what are my g of x values? What would they be? Sam. Good. Okay. Okay, so this is all you see of the graph, right? If we were just plotting points. If we were just plotting points, that's all I see. But can I figure out what the other points would be to make it a complete U? So I have this point here, negative 1, 1. Can I mirror it on the other side? What would it be? Josh? 3, 1. Also be 3, 1. Okay? And then we would have 4, 6 as well. So continue. Okay. So looking at this graph, it's the same shape. It's the same shape, even though we just have more points here. What do we notice? What's the difference from the blue to the red? Anything change? Do you notice anything? Need an answer before you go to lunch. Brian. Okay, so we moved down 3. Okay. Grace? Good. Moved 1 to the right. Okay. Can we combine those two and say something else as well? Yeah. Good. X value same. According to this graph, X value same. Y value is different. According to our table of values. Okay. Just according to the table of values. What else? What's one thing that we could say about a quadratic? Yeah. The vertex is lower. What is the vertex? One negative 3 is our vertex. Okay, so the vertex helps us show down 3 into the right 1. Okay, so the vertex is our key component here. Okay, that's where we should always start these quadratics. All right, so on that note, in transformations, okay, you're going to see a lot of commonalities for every function we do. Okay, which is this guy right here. Okay, and I'll have the notes up here plus Desmos. I'll be doing both. So we will be using this equation. Okay, we will be changing the parent function of x squared of our quadratic. Okay, so the first thing we are going to look at is putting a number in front of x squared to see what happens. So when you pull up Desmos, okay, there's a little calculator icon or keypad icon on the lower left. It gives you so many options, okay? In the first blank here, I want you to do x squared. Okay, so x and then squared. All right, that and then hit enter. This red one on my screen is our parent function. This is what we're starting with. That's always what we're starting with, our parent function. So now, if I want to put a number, and I want you guys to do this, put a variety of numbers do different graphs if you want to, by placing a number in front of x squared. So for example, 2x squared. Try that one out, see what happens. You could do negative, you could do a fraction, whatever you want. I want you to do a bunch of different examples by keeping your first one as the parent function and seeing how these graphs change. Okay, so if I wanted to do like 5x squared, okay, you guys, I want you to do different graphs. You could do up to 5, whatever you want. Do different numbers in front of x squared and see if you could figure out what is going on. How is the graphs changing? All right. So I want you to take a minute, just enter in a bunch of different a values, this is called, and see if you can notice any changes. But I want you to keep the parent function. Good. 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 Okay. You could do a bunch of different a values. Throw some negatives in there, some fractions, whatever you want. See if you can see a difference. Okay. So from our parent function, those of you that chose a value that was larger than 1, like 2x squared, 3x squared, 4x squared, 5x squared, which you see on the screen. How did it change? How does it look different from our parent function? John?
It changes, like, if it's 3x squared, it's going to run through 1 comma 3. If it's like 4x squared, it's going to run through 1, 4, and like the reciprocal as well.
Okay, so what can you conclude? That's excellent. You figured that out, right? What can you conclude about that, though? Like looking at the shape of the graph, what's changing? Yeah.
Oh, it's going to get a little bit narrower as the number before x increases. It's going to get narrower.
Good. So I'm going to use one example that you said. So an example of 4x squared, 6x squared, 3x squared, 2x squared. If that value in front of x squared is greater than 1, the graph becomes narrower, okay? Gets closer to that y-axis. It's also called, technical term here, vertical stretch. So in the box of your notes where you see A, jot this down. If your A value is greater than 1, the graph gets narrow, and it's actually called a vertical stretch, where, like John said, you will end up instead of 1, 1, then 1, 3, 1, 4, whatever, you're multiplying your y values by that, your original y values. Okay, give me another example of an A value you guys did. Yeah, Josh.
0.
So 0, what happens when we put 0 in front? Right, so 0 times anything just becomes 0, right? Okay, so what would be another example of an A value that you guys put in? Yeah, Grace? -4, okay? So those of you that haven't done negatives, oops. What's one big change that we saw with a negative in front? Yeah, Charlotte. Good. Okay, so if your A value, there's two things happening in this graph. If your A value is less than 0, meaning it's negative. An example y equals negative x squared. What is happening is it's a reflection over the x-axis. Okay, it's a reflection over the x-axis. Also, it's opening down. So the negative tells us it's reflecting, opening down. It's a negative a value. But with the example Grace gave us, what else is happening? Negative means reflection, but we have this 4 in front. What else is happening to this graph? Does it look like the same shape? Yeah, Mustafa. It's narrower. So with A, you always want to remember absolute value. The negative is separate. The negative means reflection. The A, if it's greater than 1, when you take the absolute value, then it's a vertical stretch. So this graph that we just spoke about is a reflection and a vertical stretch. So there's 2 types of transformations happening that you would have to list. Okay? Is there another example of an A value that you guys used? Yeah. 1/2. What did you notice? Good. Okay. Okay. So if you have a fraction in between 0 and 1, so even if you have 5/4, yes, that's a fraction, but is that greater than 1? 5/4? Yes, 5/4 is greater than 1, so therefore it would be a stretch. So be careful. You are looking for a fraction, however, it has to be between 0 and 1. So for example, 1/2 x squared. This becomes wider. It's also called vertical compression. Okay. So the A value changes the shape of the graph, meaning narrow, wider. It also changes the direction of where this graph is opening, either opening up or opening down. Okay. The next thing is H. Okay. So when you do this, okay, it should look like this: x minus a number, x plus a number squared. Okay. So starting with your parent function. Try different values. X minus a number, but I'm just showing you with the parentheses. All right, what do we notice? Yeah. Okay, what type of movement is happening? Yeah, Charlotte. Which sounds weird, right? Okay. So excellent observation. All right. So if I had x minus h squared, that said it was moving to the right. Okay? If I have x plus h squared, that's moving to the left. Because if I was to set whatever inside the parentheses equal to 0, is my h positive or negative? If I had x minus h equals 0. That's why it moves to the right. Okay? The h is actually positive. It's opposite of what you see. Okay? Because it comes from this. All right? If I was to have x plus h and set it equal to 0, I would get negative h. So in that parenthesis, how it got positive is if I have x minus negative h, what happens to both those signs? Comes positive. Okay? This is the only tricky part. Where you have in parentheses only affects the x. If it's x minus h, you're moving to the right. If it's x plus h, you're moving to the left. That's where it's opposite of what you see. Only for that one. Opposite of what you see. Okay? So we did changes in shape. We did changes in x, which is left and right. What's one thing that we haven't done yet? Changes to y, meaning what? Okay. So now, the last piece is our k value. So if you notice, h is inside parentheses. K is on the outside. What do we notice? This should be fairly simple. We saw it in some examples as well. Yeah. Good. It changed it by doing what? Where are we going? What's happening? Good. So if it's a positive k, like x squared plus 3, you're translating up. You're moving up the y-axis. If it's minus k, meaning x squared minus 5, you are moving down. Okay? Yeah, yep. So the k value, up, down, h, left, right, a changes the shape, narrow, wider, or reflection. Okay? These are all the transformations you will need for the entire year. So it's not only just functions, it's in polynomials, it is in exponentials, it is in trig. All these will mean the same thing. Okay? Any questions? Okay? So Desmos, if you went through and typed a bunch of different, and I saw a bunch of different graphs as I was walking around before, it shows you how the shapes change. You always want to refer back to the parent function, which is x squared, and what changes against that. Okay? So you can put your Chromebooks down or put the tops down. You don't need them. And if you guys missed anything as I was going through this, I am recording this, as you could tell, for this reason. Quadratic function. Let's see if we remembered some of this stuff. Okay? And can fill out the blanks. So, here's our quadratic equation. We know the vertex now is HK. Okay, the vertex is made up of HK which we saw in the warm-up example, actually. Okay, HK makes up our vertex. So A indicates if the graph is opening up or down, meaning if there's a negative in front, it's opening down, both arrows down. If it's positive, it's opening up. What else does A tell us? That was weird. Yes, Josh. Good. Vertical stretch or compression. And if there is a blank over the x-axis, what else does A tell us? Yeah, Phoebe. Good. A reflection. Okay. Then we have H. It indicates a horizontal translation. Shifting in what direction? Yeah, Laura. Left or right? Good. Then K indicates a vertical translation. Yeah. Up or down. Good. Okay. And again, these will be the same as we go through it. Okay, so we have our horizontal translation, left or right, vertical, up, down. Okay, so we're going to try some examples. Identifying A, H, and K. Okay, and I'll put this again on the board. Okay, so I want you to identify what is the A value in this first one. Same. 1. What is the H value? 2. Good. Excellent. Remember, x minus 2 equals 0. What is my K value? Charlotte? 4. Good. So, since I determined A, H, and K, what is my vertex? Andrew? 2, 4. Good. So before we graph our new function, I want you to graph the parent function first, which is 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. Yeah. Yeah. Okay. So now, if I graph the vertex first, it's 2, 4. 2, 4. Here's my new vertex. So we went from the origin to 2, 4. How, right then and there, how did that transform? Yeah. Good. Okay. That means all those 5 points that I graphed will be doing the same thing. Okay. So if I take this point here at negative 1, 1, move it to the right 2, and up 4, it's the same on the other side. The shape stays the same. Okay. Yeah, Grace. See the squared term here. Okay. That's automatically x squared. So the parent function is going to be from that pink sheet. Okay. So if you have square terms, so this whole page is x squared. Okay. So if we have a square term, that's x squared. If we have 2 lines like this, that's absolute value. If we have a 3, that's cubic. If we just have x, that's linear. If we have square root anywhere there, it's the square root function. Okay? Yeah, Liz. Always for this. Always. Your vertex will always be hk for quadratic functions. Okay? Your vertex will always be hk for quadratic functions. Okay? So now, if we look at number 2, what is my a value? Yeah, -1. Okay. What is my h value? Yeah, Kima. 0, because there's no parentheses there. What is my k? John? 3. So therefore, what is my vertex? Brian? 0, 3. Okay. So before we graph anything, looking at my equation, what types of transformations are happening? Who can name one? Give you guys a minute. Who can name one? Phoebe, give me one. Up 3. Josh, give me another. Good. So, one thing I will add. Will you always have to, excuse me, graph the parent function? No, not until you're good at this, which you will be very soon. Okay? The parent function just helps us understand the transformations that are happening. So, that's my parent function. I know my vertex is 0, 3. Okay? I know my vertex is 0, 3. But if you notice on the green function, from the original vertex, I go up 1 to the right and up 1 to the left. Am I still going to go up? No, which direction? Down. Okay? Then, if you go back to your vertex, and I go up how many until my next point? 1, 2, 3, 4. Over how many? 2. But instead of up, where am I going? From the new vertex. 1, 2, 3, 4. Over 2. Some people might ask, well, can I do this by using a table of values? Absolutely. You could. You could plug in x values. However, if you notice from the first warm-up, we used the same x values. However, our graph was 2. We only saw one piece of it, right? So, anytime you want to use the table of values, if you wanted to use the table of values, you start off with your vertex in the middle. You choose 2x values below and 2x values above, meaning, and it ends up being the same thing. Therefore, you only have to figure out these 2 points, 2x values, in order to find these. Okay? Try the third one. Oh, question.
So, is it always going to be reflected in the a value?
Always. Yep. Okay? Try number 3 on your own. Okay, for the third one, what is my a value? Grace. Good. What's my h? Mustafa. Careful. Okay, okay. Lily. -3. Remember, it's the opposite. It's okay. It's the opposite of what you see. K is actually the same. So what is my k value? Well, -1. So what is my new vertex? Sam? -3, -1. What types of transformations are happening? Laurel? Careful. Good. Excellent. It's okay. 1. So -3, -1. And here is your new graph. Okay. Excellent. Excellent. Okay. And the last one that we're going to get to today, right? Number 4. What is my A value? Sam? H. 0. K. 0. What's my vertex? Yep. 0, 0. What kind of transformation is happening? Yeah. Good. Vertical stretch. By 4. Okay. So I'm just going to show you. So what do you think? The last thing we'll get to. Okay. So if it's a vertical stretch, what values are going to change? My vertex is still 0, 0. Yeah. The y value. So what would I have to do to show a vertical stretch then? What does that mean? Yes, the y values are going to change. Yeah. Good. You multiply the y values by 4. So instead of 1, 1, where's my next point? 1, 4. Then I also have -1, 4. Oops. And that's your graph. Okay? All right. You guys did